All right, let's get going then. Okay, so today we have two more examples of divide and conquer, and I think that'll sort of be it for divide and conquer. This is probably the last time I'll show this, just to see if there's any more questions about the syllabus or logistics. I want to add something. I made one modification, which I think nobody will mind. We had this rule that we drop 20% of the homework problems. That used to just be the word problems, but I think we'll just throw the multiple choice in there as well. Because I know somebody's going to forget to do multiple choice tonight, and then they're going to email me, and it's going to be awkward because the answers are already out, all this nonsense. So, like a weekly multiple choice would just be treated as like one word problem. They're all worth kind of 10 points. So that's just like part of the n when we drop n over 5. So it'll be n over 5, lowest either multiple choice or word problems. Yeah.
So just do all the parts of one word problem kind of one word problem.
Yeah.
Like
Then the multiple choice will have like, some number of smaller questions, and that'll sort of be like one word problem.
so one exercise number is worth 10 points or
Yeah. I guess so. Yeah. We just try to keep it all the same, so it's simple. Okay, so yes, I think that's only in people's favor, so hopefully there's no complaints. It basically means you can skip more stuff. Yeah.
extra word list.
Probably tomorrow. Yeah. It'll almost certainly be what it is. Yeah. Okay. Anything else? All right, on to the fun stuff. Okay, so here's something you've all done a million times. Why are we even teaching this? But we're going to discuss first an algorithm for multiplying n-bit integers. Okay, so here I give you two integers, but in binary. Okay, and your goal is to just multiply them together, right? So I guess here's some example I wrote out. How do we do multiplication in grade school? Presumably you've all been through grade school. All right, we're off to yeah. Yeah.
Start with the rightmost digit of the
Yeah, this guy here. Yeah, so something like, okay, this is like 32, and you carry some 3, and you get 24, 27. I might make a mistake. 16 becomes 18. You carry the 1, you get like 9. Is that hopefully correct for the first row? And then you move on to this one. 7 times 4 is, I hope, 28. 21 plus you carry a 2. I think that gives you 23. You have 14, you're carrying a 2, you get 16, 7, 8, something like this. And you keep going. Is that wrong? I don't know. Okay, but this is what we do. And then we keep doing 2 more, and then we add them all up at the end, right? 2 will come straight down. You get like 15 here. This will depend on the next row, but okay, so we've all done this. All right, so how long does this take? If I had done the whole thing, or if there's more than 4 digits as a function of bits. You can imagine doing this in binary, right? It'd be the same thing. Yeah. It's going to be n squared. So ultimately, everything down here gets multiplied with everything up above. And then you add some stuff at the end, but that's not so bad. Okay, so you'll end up spending n squared time. And of course, the question is, can you do better? And there are some historical significance to the problem. So has anyone here heard of a guy named Kolmogorov? So this is like a very famous Russian mathematician. Solved a lot of, one of Hilbert's problems. He also sometimes gets credits for like formalizing the axioms of probability theory, I think in like 1920s or 1930s. Probably he's not as old as you'd think. But in the 1950s, he's in Russia. I guess he starts getting interested in computing. Whether or not they had computers, they certainly knew it was on the horizon. And so he conjectured, I guess he had some kind of seminar going, and he conjectured that you can't do better than this n squared multiplication. Because, I don't know, we've been doing it forever, and I don't think anyone ever second guessed this kind of thing. So that was in the 1950s. And then in 1960, I think he was a grad student at the time, but his name is Karatsuba, also I think a Russian, came up with a faster algorithm. Okay, and that's what we're about to do. But I think that a really important takeaway is at some level, nothing could have been simpler than multiplying integers. And here you have like the world's foremost mathematician saying, yeah, obviously this is the best you can do. And just the fact that you can do something better, okay, makes you revisit a lot of stuff. Like, oh, okay, there's something slightly different about kind of math and computing and things like this. And there's maybe a little bit more to the eye. Okay, so this was I think a very surprising thing at the time. But okay, since you don't know his algorithm, you can for a moment pretend to be Karatsuba sitting in the 1950s, and I can pretend to be Kolmogorov. But anyone want to take a stab at a better than n squared algorithm for multiplying integers? Yeah.
Split it into two somehow, and then like multiply them, and then like you.
Okay. So we can try dividing the inputs in half, something like this, right? So, okay, so here's my two n-bit strings. I divided x into two even parts, x1, x2. For simplicity, assume it's a power of 2, the number of bits. I've split y into y1 and y2. So if you want to kind of recover it, x would be x1 shifted up n over 2 bits, multiplied by 2 to the n over 2, plus x2. Y is y1 shifted up n over 2 bits, plus y2. Okay? And if we do the thing we've all done a million times, right? I write x times y, but I first, plug in and expand out, you'll get something like this. Plus you'll get these two cross terms in the middle, plus the last term. Okay, this seems like a natural thing to do. Okay, so let's maybe analyze, is this what you had in mind? Okay, so let's analyze the running time of the algorithm. Or let me be clear about the algorithm. Once you split it up, then I think the idea we all have in mind is to recurse on each of these smaller individual integer multiplication, right? Okay, good. So what would be the running time of this algorithm? Let's first model it, and then we'll do our usual recursion tree. Yeah. 2tn over 2. Maybe you need some O of n to add things up at the end. Is this what everyone else got? Okay, so 2tn over 2. That means there's two multiplies that have n over 2 bits. What are the two multiplies? This one? Is that one? Then that would be another one. Okay, but then what about this one? I think we need more than 2. 4. Okay, so not everything in this class looks like merge sort. Okay, so we have something like this. Okay, so I just kind of divided each integer in half, big half, small half, and then you have basically 4 different products to all possible pairs. Yeah. Yeah. So take the top row. We have x just as an n-bit string, and we want to try to divide and conquer. So a natural thing to do is to try to divide the upper half of the bits, the n over 2 most significant bits. That's on this side for you, and the n over 2 least significant. And so this is an n over 2 bit number, and that's an n over 2 bit number. And if I want to put x back together, I don't just add them directly. I would do x1 times 2 to the n over 2, right? Because that kind of adds the zeros. So this is just shifting. Okay. But anyway, so that's a divide and conquer. Now, I think the most natural thing to try to do. And now if we start writing a recurrence tree, right? My top problem has size n. Then I have 4 problems of size n over 2. Then I'm going to have, each of these will have 4 problems of size n over 4. Okay. Something like this, and it'll go on and on. Okay, so the top row, how much total work do we do excluding recursive calls? N. Okay, how about the second row? 2n, right? 4 times n over 2. And what about that third row? 4n, because that is 16 times n over 4. Yeah. And in general, if you were at like row I, what would it be? You'll be looking at something like 2 to the I n. Okay, we sum all that up. How tall will this tree be? Log base 2 of n, because each time we divide by 2. Okay, so if we added everything up, we'll get something like this. For log n levels, I just keep doubling the total amount of work. Okay. All right, so what does this sum come out to? N squared. Okay, it's going to be dominated by the largest term. That's 2 to the log base 2 of n. Okay, that's n. You already had an n. Now you have n squared. Okay, so that just got us back to the original algorithm. Yeah. Yeah, so I threw in a plus O of n because I figured after we even did all these pairwise multiplications, you'll now have 4 terms you want to add together. So just the addition at the end. So you can recurse to get these individual multiplication, but then we have to add it together to make a n-bit number.
Maybe I misremember it, but I thought that was O of log n.
Okay. That's a good point. So this is already n-bit integer, so it's between 1 and 2 to the n. In the past, we we're always talking about, or last time we talked about integers between 1 and n, which took log 2n. So we've kind of scaled up, because it's more natural in this case to just focus on number of bits. Good point. Okay, is that okay? So the natural divide and conquer actually does nothing different actually than our sort of natural school, 5th grade multiplication. Okay, still it's a reasonable idea. Any other ideas? Okay, I'll give a hint. There's no hint here. Is there? No. Okay. Okay, so yeah, okay, here's my hint. This is slightly different, right? Because I've removed that 2 to the n term in front of x1 and stuff. But just look at x1 plus x2 times y1 plus y2, and you'll get this factor of, 4 things. This is just arithmetic, right? All right, does anyone notice anything conspicuous or useful about this? Yeah. Sorry, just a little louder. Yes. So look at this in the middle, these middle terms, right? This is the cross term that also appears normally, okay? And the 2 outer terms, you're going to, did it freeze? You might compute anyway, right? You were planning to do x1, y1 and x2, y2 anyway. So if you've already computed x1, y1, x2, y2, and you're just trying to get at the middle term, then what can you do? Yeah. Or either. Yeah, so we can rewrite something like this. Okay, we can get the middle term by multiplying this mysterious sum, right? x1 plus x2 is not x, just something. Well, we can multiply them together and then subtract out, that should be a subtraction, subtract out what we were going to multiply. anyway. Okay, a very cute, simple trick. But the nice thing is that you're basically getting two multiplies. You're getting the whole cross term for the price of just one more multiplication. Okay? So whereas a natural thing, you end up with 4 multiplications of n over 2, Karatsuba should notice that, oh, you can actually do it in 3 multiplications. And here we're going to kind of leverage the fact that adding and subtracting is much faster. Right? Adding and subtracting is not quadratic, it's just linear. Okay. So that's the algorithm. That's the trick. Now let's just analyze and make sure it's correct. Okay, here's the kind of standard thing I force everyone to do. We're going to make a recursive algorithm. So if we first need a recursive specification, we just name it, give the parameters, describe it. Who wants to put one forth? All right, who wants to name it? Yeah. All right, we'll call it multiply. And what are my parameters? Yeah, x and y. Okay, great. Just want to define the thing we're going to implement. Yeah. Yeah, we're just going to multiply. Maybe I'll first describe what the input is. Given two integers x and y, return their product. As usual, it's not so different what the original problem was, but you do need to establish this to feel good about your recursion formally. Yeah. Do you still have to? Trying to think of examples. Yeah, well, there's not going to be maybe as many iterative algorithms as you might expect in this class. Yeah, not clear. At some level, it seems hard to prove anything. Here's my function. I'm going to prove and say something about it. It seems very hard to skip the step where you describe what goes in and what goes out. So it may not play as critical a role, but at some level, I don't see how you can basically skip this information anyway. So maybe it's just good practice to play it safe. Yeah, from a teacher standpoint, you'd be surprised how many mistakes are just basically rooted at not clarifying the input and output. You see some solution, you know the right answer, you reverse engineer, it's like, they just took a little more time here. Probably would have been fine. Okay, that's all I had. Something like this. Okay, so now maybe we want to implement it. I guess we already know what the algorithm, so I'll just show it. As usual, I think the pseudocode makes it look way worse than it is. But I'll just go through it slowly. If there's 0 bits, just return 0. That means you have 2 zeros. If there's 1 bit, I'll just multiply them together. So I'll address some base cases. Okay. Otherwise, I don't know. This is how I did it, but you didn't have to. I first said, okay, if n's not even, let me prepend a 0 and make it even. But you didn't really have to do this. In other words, I'm going to split x into its 2-bit strings, so y into its 2-bit strings. And then here we're doing the x1 plus x2 and the y1 plus y2. Okay. Yeah, question?
The test specification is for select and not multiply.
That's a very good point, isn't it? Okay, sorry about that. The weirdest thing is like, I gave the same lecture last year. No one seemed to mind. Okay. All right, that's very helpful. Okay, but just continuing, I feel like I'm just being maybe conservative to keep track of exactly how many bits we're using. That's why notation is kind of so annoying. But here I'm adding x1 plus x2 together, y1 plus y2 together, so that we can do that trick. And now we're just recursing. I'm multiplying x1 and y1, x2 and y2, and x3 and y3. Okay, and this is where you're really using a recursive spec. You're guaranteed that your subcalls to multiply will multiply. Okay, that's the contract. And then finally, we do that arithmetic that we mentioned. You're going to take your x1, y1, multiply, shift it up by n bits. Here's that cross term obtained by that subtraction trick, shifted by n over 2 bits. And then you add in that last thing. Okay, I feel like the code just makes it look more messy than it really is. We're just splitting and doing the Karatsuba trick. Okay, we're okay with the algorithm? You know, as far as correctness goes, this is just a straightforward proof by induction. You just want to prove that your algorithm implements a recursive spec, which you've already declared. The base case is n equals 0, n equals 1. That's clearly okay. And then, you know, assuming that the kind of arithmetic we did together a slide ago is just fine, then you can clearly see, okay, knowing by induction that I do get the right product of x1, y1, and x2, y2, and x3, y3, then this is what I'm looking for. Okay, so induction is happening here. That guarantees your subcalls will multiply correctly. Okay. Is that it for this? Oh, no, we have to do some running time stuff. Okay, but any questions about the algorithm? Okay. Then let's analyze the running time now. Maybe this is too small to see. So what is the running time of our algorithm? Oh, that doesn't look good. Oh, that's why, sorry. Okay, what can you do? Okay, so what's the running time of our algorithm? Maybe I can go back up to here. First, we want to just model it. Yeah. Okay, now we have 3 times t of n over 2 plus big O of n. If I was going to be more careful, it's kind of more immediately 2 times n over 2 plus 1 n over 2 plus 1, because x3 and y3 may have one more bit from adding things together. But the plus 1 is not going to change anything. Yeah.
Which property exactly lets us split given numbers into 2 different?
Yeah, is there a name for this property? So this is coming back to here. Does anyone know, is there a name for? So to me, this is just, I'm willing to take for granted that, you know, any number I can split into a bigger and smaller part. I don't know if there's like a, you know, name of a Wikipedia article for this property. Anyone know?
Maybe I'm thinking into the semantics of it too much. Because I know like edge cases like signed and unsigned integers.
Oh, okay. So we're only worried about positive integers. If you want to extend this to signs, I think you just move the sign out and you do that on your own. And I'm assuming that kind of we're okay with binary. And we're kind of okay with statements like, you know, yeah, I'm kind of taking all this for granted. And yeah, if we're not comfortable with binary, then we might have to take a big step back, right? But like basically I think it's fine. Yeah. So at some level, let's say, yeah, I mean, I don't know if there's a name of property. This is just, you know, one way to interpret bits, right? We can always reassemble bits and stuff like this. And I think it's an encoding of integers. Yeah. Okay. Any other questions? Yeah.
Why we plus 2 there to runtime?
+2. What I was saying about maybe this should have +1.
Yeah.
Yeah. So when we, you know, that's really referring to this multiply here. Okay. So if I add, you know, 2 10-bit numbers together, you might have to carry the 1. So you might just go up to 11 bits. Okay. So that's right. So if we wanted to be like very careful at first, you know, you might more properly have 2 tn over 2 plus 1 term of n over 2 plus 1. but the plus 1 can be ignored. Okay, and so we end up with 3tn over 2, which is probably what you had in mind anyway. Okay, so good. All right, so let's just solve this recurrence tree. Okay, we have problems of size n at the top, n over 2. This will become n over 4. Right? So I'm just writing out the problem sizes. And then we just tally up the work on each level. How much work do we spend on top level? N. And in the second level, 3n over 2, not a trick question. What about the next level? Be 9 over 4, or 3/2 squared. In general, if I'm looking at the ith level, you might think it's 3/2 to the I, something like this. Okay, good. All right. Oh, I meant to ask, and how tall is this tree? Log base 2 of n. So here the base will matter, as we'll see. Okay. So now just some arithmetic. Okay. What does this look like? What does this evaluate to? Up to constants? So this is what our tree added up to, right? Yeah. Yeah. Yeah, so up to constants, this sum is always going to be dominated by the largest term. Okay. And now we just have to clean this up. Yeah. So, I'm very clumsy. So I would just write something like, I would convert the 3/2 to 2 to the log base 2 of 3/2. Okay. Times log base 2 of n times n. Okay, so I just put the 3/2 up in the corner. And now it's easier to just bring down this n. So you'll get something like n to the, maybe I'll go slowly, log base 2 of 3/2 times n. Okay, so to maybe go a little bit more slowly, up in the exponent, I can first kind of reverse the order of these two. Put the log 2n on the inside, and then 2 to the log base 2 of n is n, right? Just by, that's what logs are. Okay, so now you're left with something like this. You really had a log base 2 3/2 in the exponent. We can clean this up a little bit more. So log base 2, I mean, it's not super exciting to just take logs all day, right? If I remember correctly, this is log base 2 of 3 minus log base 2 of 2, right? That's the rule. And what's log base 2 of 2? 1. Okay. So this minus 1, so this will look like log base 2 of 3 minus 1. This minus 1 can just cancel out with that n we already had. And we're left with big O of n to the log base 2 of 3. Whatever that number is. What is that number? I think it's like 1 point. I have it written down. Okay, so apparently it's about 1.585. And by the way, obviously, if it's like an exam or something, you just have to leave log base 2 of 3. You don't have to do any logarithmic calculations yourself. Okay, right? But the point is, this is obviously, significantly faster than n squared. Okay, and that was sort of the big surprising thing at the time, that you could take something as basic as multiplying integers and get a significantly faster running time. And then you start wondering about everything else you took for granted. All right. Any questions? Great. Okay, so here, okay, the next one is a little bit, well, it has a little more math prerequisite, but I'll go over it slowly. And is maybe more, anyway, it'll be a little fancier, but it's not so bad. So this is about something called the Fourier transform. Okay, what the hell is the Fourier transform? Who knows? But it's going to involve complex numbers. So I imagine you've probably been exposed at least slightly to complex numbers before, but I'll kind of go through things slowly, just enough background to, interface and understand the algorithm. Okay, so you're not going to be tested on complex analysis. It's just enough to explain things. Okay, so as you know, complex numbers have like a real part and an imaginary part. You can kind of imagine them living on an XY axis. Okay, the real part, the imaginary part, right? That I is imaginary I. It's the square root of -1. It gives you like a complete algebra or whatever. Okay. So, okay. So I think you know something like this. If you want to multiply two complex numbers together, the first two parts should look familiar, right? AC, that's multiplying A times C together. Then I have the cross term in the middle. Now BD got negated because I squared is -1. Okay, so just one small thing compared to what you're used to. But as soon as multiplication is well defined, now we can talk about polynomials of a complex variable, right? I know how to evaluate a polynomial of a complex variable because I know how to multiply complex variables together. Okay. And then once you have polynomials, that means you also have things like anything that can be expressed as the limit of polynomials. So you may have seen this before, but the exponential function e to the x can, this is sort of its Taylor series, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. The limit of that as you go on and on and on, that is e to the x. Okay? And so if you're wondering like, well, I don't really know what it means to exponentiate a complex variable, you could just look at the polynomial. Okay? This will converge to whatever the value is. Okay, so good. Now, so Euler's formula is sort of this famous thing. So for any value of theta, and it could be modulo 2 pi, okay, if you plot e to the theta I, like what is this value? Okay, the real part's actually going to be cosine of theta, and the imaginary part is going to be sine of theta. Okay, so e theta I is actually spinning around, from your point of view, spinning around counterclockwise. Okay, spinning around counterclockwise. Okay, and what else did I write? That's right. So for example, Euler's identity, if you did a full pi, okay, and you did it 180 degrees, you'll end up at -1. Okay, and if you did 2 pi, you'll spin around and get back to 1. Okay, so that's one way to think of, e to the x of I, or x times I, is actually spinning around the circle, around and around and around and around. I won't prove this, but we'll take it for granted. I think that's all we'll need to know about complex numbers. Well, I guess you need one more. Okay, so there's this notion of a root of unity, which is going to be very useful for us in this Fourier transforms. Just one more slide about complex variables. So an nth root of unity is any number where if I took it to the nth power, I get 1. Okay. So like, what are some examples of roots of unity? E to the what? Yeah, pi. Okay, that's pretty sophisticated. So somewhere up along this circle, pi over 4. So that would put you actually pretty close to here, right? Something like this. So let me draw a different color at least. Let's say that's roughly 1/8 of the pi. It should be 1/8, right? Pi over 4. And so if I kind of kept going 1/8 at a time, and I ticked around I guess a total of 8 times, I'll get 1. Okay, so that 1/8, whatever o'clock that is, that would be an 8th root of unity. All right, so you skipped all the like more obvious ones. So for example, 1 is a root of unity for any n. Okay. -1 is a root of unity for like 2 or any even number. Yeah. Oh, well, I'm saying that. No, it's not. Okay, this is not really great syntax. I'm saying that 1 is a root of unity for any, and an nth root of unity for any. Oh, yes. Okay, I think that was pointed out last time. I just forgot to. Sometimes I make the same typos every year, but it keeps them on their toes. Okay. All right. Very simple. -1, and then the next simplest one was maybe imaginary I, right? I to the 4th. I squared will get you -1. You square it again, you get 1. Okay. But as pointed out, because of this very nice Euler's identity and the fact that you're going around this circle, and you can go around the circle kind of as many times as you want. If I want to get like the nth roots of unity for any n, maybe an awkward n like 17 or something, I guess here is 16. I can divide the circle into 16 equal parts, right? And so this will just tick around, and after 16, I'll get back to here. But as well as any of these others, right? This is an 8th root of unity, so it's also a 16th root. But even if you went to the 3/16, okay, you'll get an nth root unity by the time you go around n times. Okay, so that means each time you go 3, 3, 3, 3, 3, 3, but you'll end up at 1. Okay. So for any n, there's kind of these n distinct points where if you take it to the nth power, you get 1. Okay, this would be it for 16. You can imagine 32, you can imagine 64, where I just keep refining it. Okay. So complex numbers has this very cute trick. Doesn't seem very useful right now, but it has this very cute trick where you can get many roots of unity. You can get 64 64th roots of unity or whatever, and they're all distinct. If you're restricted to real numbers, you don't get this. Okay. All right, so that's all the complex values we need. It's just basically this roots of unity, which is leveraging the circle trick that occurs as complex numbers. Okay. All right, so now let me explain what the Fourier transform is, which first would just seem technical and kind of useless, but I'll give an application in a moment. So you're going to take as input n numbers, but one way to interpret that is the coefficients of a polynomial. There's probably a typo there. Okay. So you're given n numbers. Okay. And I'm going to interpret it as the coefficients of a degree n-1 polynomial, which has n coefficients. Okay. And what the Fourier transform is going to do is it's going to evaluate that polynomial at the nth roots of unity. Okay, so it's just going to take a polynomial and evaluate at n different locations. It doesn't seem very special. Okay. But naively, if I had a degree n-1 polynomial and I wanted to evaluate at n different places, how long would it take? Assuming arithmetic takes constant time. Well, how about just one value? If I wanted to evaluate a polynomial of degree n or n-1, it'll take like n time, right? Because I have to plug into each place, do the multiplication there, and then add things up. Okay, here I'm just going to take multiplication as ignore the first part of the lecture. We'll treat multiplication as a constant time thing again. Okay? But what we're going to try to do is we're going to try to do that much faster if we do the roots of unity in particular. Okay, and only in the aggregate. Okay, so in addition to the Fourier transform, there's a conjugate Fourier transform. Okay, and it's very similar. It has the same input. It takes some n numbers. We think of that as a polynomial, and the output is almost identical. Okay, it's going to be n values, and you're going to evaluate all the roots of unity. Only the output, it's going to see the first one is kind of going clockwise around the circle. and this one is going counterclockwise around the circle. Okay, so it's not very different. From a computer scientist standpoint, it's like, what's the difference? Obviously, if you can do one, you just reverse the input, reverse the output, you get the other. So implementation-wise, they're the same. Okay, but there is this thing called the conjugate Fourier transform, and it's really just this opposite rotation. Why do I even mention the conjugate transform? Is because it's basically inverse to the discrete transform. Okay, I won't do this proof because it's just math and you just watch me cancel out terms. But if I apply the Fourier transform to A and it evaluates this polynomial at these things, and then I basically evaluate it, so then I get n values, right, from the Fourier transform. Then I think of that as coefficients of another polynomial, and I evaluate it again at all these nth roots of unity. Only this time I list the outputs kind of going clockwise instead of counterclockwise or something. I'm very confused, but you get the point. You will actually recover your original values, your original coefficients, scaled up by a factor of n, which of course you can divide out. Okay, so basically the same operation is almost the inverse for itself. Okay, so right. Okay, so we have this Fourier transform, conjugate Fourier transform. Not at all clear why I've kind of dragged you through all this stuff. So, I should mention that Fourier transforms used all the time in like signal processing and things like this, but I'm not really an expert on anything real. So, okay. So naively, it takes n squared time to evaluate all these things. We're going to get it down to n log n. Okay, so that's what we'll focus on. Right? So clearly that's much better than naive. That's like sorting. That's very fast. It's much faster than our integer multiplication. Okay. This is assuming, constant time arithmetic. Otherwise you have another, log factor for the bit complexity. But let me give an application because it's not clear right now why we're even going through this, except for the fact that you've probably heard of the Fourier transform before, so it sounds important. But here's maybe a simple thing that at least makes more sense to me. Suppose I have two polynomials, and I just want to multiply them together. Okay, so two, n degree n polynomials, or just make the smaller one bigger with a bunch of zeros. So I have two degree n polynomials, and I just want to multiply them together, right? So I have p and q, and I just want to get p times q. That too naively could take n squared time. Okay. All right, so how can we use the Fourier transform? Okay, so the coefficients of R, if we look at it, more closely, right? R will have some coefficients C0, C1 up to C2n minus 2, right? But what do those coefficients actually look like? They look like this convolution. So if I'm looking at like the 10th coefficient of my output, right? These are all like, I take one term from one polynomial, one term from the other, and I get degree 10, right? So that means it's going to be like A0 times B10 plus A1 times B9 plus A2 times B8. It's kind of zip things together. Yeah? So it's this kind of convolution thing. So again, that's the standard formula. It would take n squared time to do all of these directly. Okay. Does anyone? Okay, so I'm claiming that we can use the Fourier transform to multiply two polynomials together much, much faster. Does anyone want to take a crack at it? Yeah.
Evaluating the points and then fit the new curve to it, like you evaluate each of them at enough points. You just multiply those points together and fit your polynomial.
Yeah, kind of. Okay, so can I do something with the values? You might know that like if you know the value of a polynomial at n different points, you can recover the entire polynomial. So if I can kind of like, okay, good. But there's some values that are algorithmically nice, especially given what I've already introduced and things like this. For example, okay, so you know that the Fourier transform is fast. You know the conjugate Fourier transform is fast. If I had the Fourier transform of R, which is to say I know the value of R at certain points, these roots of unity, I could apply the conjugate very fast and recover R. So that special case, I can do the interpolation very easily. Okay, so I know that if I had the Fourier transform of R, which is that mysterious kind of thing, I could get R easily with the conjugate Fourier transform. So now how can I get the Fourier transform of R? That is evaluating R at each of these n roots of unity, yeah.
So you can do the Fourier transform P and the Fourier transform Q and then multiply all the results together. Like one by one.
Perfect. So if I want to know, what is the value of R of omega, well, I can compute P of omega and Q of omega and just multiply them together, right? And it turns out, for the n roots of unity, I can compute all of them in the aggregate much faster than as if they were kind of individual. So the full pipeline will look something like this. So I start with P and Q, and I'll make it 2n just to make sure there's plenty of points, because P times Q will have higher degree, right? So you need to make sure it's enough. But you just spend n log n time, applied to the vector of coefficients. And that's giving you the values of P and Q at each of these 2nth roots of unity. Okay, so you're getting 2n values in just n log n time. And now that you have those values, you just go through and you multiply them together. P of omega times Q of omega, P of omega squared times Q of omega squared, P of omega cubed times Q of omega cubed. Okay, something like this, right? But you're just kind of zipping these values together, so it only takes n, 2n time. You just one multiplication, one. Okay, so you're just zipping things together. You're not doing like all pairs. And now you have the Fourier transform of R, or its coefficients. And you can apply this conjugate Fourier transform and then divide by 2n or whatever to scale down appropriately. That's easy to do. Okay, so it's a very nice trick. So we start with the two polynomials, and then we kind of go into this value space, right? We evaluated all the roots of unity, and that particular set of values we can do super fast. And now that we have those values, we can get the values for R. Right? So we're able to get all these values for R without explicitly constructing R. And now that we have the values at each of the roots of unity, I can flip it back to recover the actual coefficients for R. Yeah.
When we say like f like 1 times its conjugate, one exactly is like a pairwise multiplication, like online multiplication, or what exactly?
Going from here to here?
No, like the fact there, but like the conjugate times.
Okay. So think of it as a function. So f of n takes a and spits out some vector, right? And then that vector gets fit into fn star. So maybe I should have drawn parentheses. So if I maybe, I don't know if this helps, but you could have a parentheses here, right? Fn takes in a, it spits out another set of vectors, which is all those values. And if you applied it again like this, you get this. Okay. So I just didn't write out the parentheses. Yeah. Yeah. Okay, so I'm taking a degree n polynomial, putting into something that expects a degree 2n polynomial. So here, a degree n polynomial is a degree 2n polynomials with not very interesting coefficients. It's just 0, 0, 0, 0, 0. So that's okay. You just feed in zeros for the omitted coefficients. That's no big deal. Yeah, so discrete Fourier transform for some n can handle anything up to n. Okay, simple enough, right? Any questions? Okay. All right, so let's now talk about how to do this and maybe leverage a little bit of the complexity, horrible complexity, or complex analysis I exposed you to. Okay. All right, so again, the main idea is just, okay. So here's the key idea that we're going to leverage, and then maybe you can keep an eye out for where we can really insert it. Okay, so one thing really nice about the roots of unity, okay, if I look at like the 2nth root of unity and I square it, if you think about those ticks on the circle, right? I have just one small tick and I square it, then I'll get like the nth root of unity, for half as many roots. Okay, so if I had like a 30-second root of unity, the first one, so it's like 1/32 the way through the circle, and I square it, then you'll get 1/16 the way through the circle, right? Because it's just a rotation, right? So the 32 roots of unity, when I square them, I get the 16th roots of unity. When I square those, I get the 8th roots of unity. When I square those, I get the 4th. So there's this kind of very nice pattern for roots of unity. So keep an eye out for maybe where we can use that, because that's going to be the one sort of trick we need. Okay, a lot of these divide and conquers, you need one structural observation, some trick, and then we just have to put the algorithm together. So that's going to be the trick. So, okay, so let's just go slowly. So, okay, so if I just plug things in, right? This is just I'm evaluating at all the 2n roots of unity, and at some level I'm going to try to recurse and get it down to n roots of unity, but we'll see. And so, okay, that's just a definition. And yeah, this is a definition in particular, for the kth one, right? You're going to output 2n different values. This is number k. And I can break this up. So what I've done here is I split it in half. So on top, I have sort of all the even degrees and their coefficients. And in the row below, I have all the odd degrees and their coefficients. So I'm just rearranging terms. Nothing has really happened. That's okay, right? Okay. Now what? Okay. So let's look at nothing down here. Okay, so let's look at the even terms first. Okay, so I think I just repeat this down here. Okay, so let's just look at the even terms. What can I try to do with these even coefficients and even degrees? If it's simpler, you can just think of k being 1. Yeah. Okay, so I have all these even powers, right? So I can square this, I can square that, I can square everything. Okay. And what you're left with is now you're just looking at the nth roots of unity, and all those degrees have gone down by a factor of 2. Okay, so up here I had degrees 0, 2, 4, 6, 8, 10, 12. And then I square it, the roots of unity, and now I have 0, 1, 2, 3, 4, 5, 6, but I'm evaluating the nth roots of unity instead of the 2nth roots of unity. Really, 2n means you're dividing the circle into 2n pieces, so it's kind of like a smaller piece of the pie. Okay. All right, so in that sense, I can kind of take our 2n degree problem and turn it into a degree n problem. Okay, and now how do I deal with this? Or what is this? Yeah. Now you can recurse. Right. So down here, now you're just looking at the kth output. If you applied the nth Fourier transform, our goal is to compute the 2nth Fourier transform. If you compute the nth Fourier transform to the even coefficients. Okay, so you bring n down by a factor of 2, and you just do that. Okay? Something like this. Okay, so that's how we deal with the even coefficients. You might imagine we can do something similar with the odd coefficients. But of course, we can't just divide by 2 because you have odd numbers up there. Right? Now I have 1, 3, 5, 7, 9, 11, 13, and so forth. Okay, but I would of course like to do a similar trick. Any ideas? Yeah. Oh, interesting. This is new. Okay. So what if I multiplied everything by omega 2n and then also divide out or something so it stays the same. And then I basically add 1 to all of these. So I go from 1, 3, 5, 7, so forth to 2, 4, 6, 8. Who do we? Okay. Right. Okay, that's actually a clever idea. I had something in mind that's very similar, but it's not multiplying in. Yeah. You can also divide out. So I can pull one of these terms out. Okay, which at least is how the rest of the slides are set up. So I'll stick with that. But the other approach might work with a little care at least. So I'll pull one of these terms out. So now 1, 3, 5, 7, 9 becomes 0, 2, 4, 6, 8 times 1 extra omega 2n at these. Yeah.
Do you plot an omega 2n to the power of k, or just an omega 2?
Oh, that's true. I would pull out to the power of k. Good point. Good. But I would pull out one of these things that we're looking for. Okay. And now, okay, now you have something like this, right? You have it down to n roots of unity with n terms, n coefficients. And so you can just recurse, do the nth Fourier transform on the odd coefficients, and then you just have to add in this term you removed. So we need those complex numbers to be able to do this kind of doubling or halving trick, right? Because it's this kind of rotations around the circle. Okay, so that's basically it. So again, you break it down into even and odd, and you write it as the nth Fourier transform over to odd and even coefficients separately, but you've gone from 2n down to n, and now you can use induction to get all those n values. So I think a lot of things we did, we kind of split in half, like upper and lower. This time we're splitting into even and odd. This is still clever. Any questions about the algorithm? I guess I have the full code here, but the full code is maybe whatever, just as. So n equals 0, n equals 1, you just do the direct thing. And then for larger n, then you'll start splitting in half. Okay, odds and evens. Hopefully that's what's written. Yeah. Hopefully that's correct. All right. Good. So let's just look at the running time then. Okay. So let's say T of n is to compute the nth Fourier transform. That means you take n coefficients and you want to get the values at all nth roots of unity. How would I model the running time? 2tn over 2 plus, yeah, some linear work just from assembling and reassembling and things like this. Okay. We've seen this recurrence before, right? It's like merge sort. So what is this? N log n. So that's how we can multiply polynomials much faster than naively. Okay. In fact, there's a whole bunch of clever things you can do. You can actually even do things like pattern matching and stuff. Anything that sort of is really, because what it sort of lets you do is it lets you compute all of these convolutions very fast, right? And you kind of get this all-to-all thing, but the running time is much faster. So people have come up with, a variety of kind of clever situations where you can leverage FFT. Yeah, I think one will be on the PSO, one will be on the homework. Yeah.
So it makes sense to use this just to multiply numbers themselves.
Okay. So this is this. I was wondering if you guys are going to raise this. So why not use this to multiply integers? Okay. So how would you use it to multiply integers? First of all, just walk me through the basic steps.
It's just you think with numbers like a polynomial where the coefficients are the It's
Yeah, so your integer has bits, and those are zeros and ones, and that's just coefficients of a polynomial: 0, 1, 0, 1, x squared, x cubed, x fourth. Okay, so you can multiply that together, and then you're going to get this polynomial multiplying them together, which is very much kind of what you want. And then you just have to carry. You just go through and carry. Okay, so in fact, you can do integer multiplication with FFT. The only reason I haven't fully written out the slide, and it's left as an exercise, the only thing that you want to be a little bit careful about is that when we talk about multiplying integers, we're very concerned with the bit complexity, right? And it's n bits. And then, okay, now you throw it into FFT, which is still doing some arithmetic and adding things up and things like this, right? So you have to spend a little bit of time bounding. If the coefficients, the coefficients won't come out that big because it's just a bunch of ones and zeros. It's at most n. So you're not really dealing with big numbers. But those granular operations in FFT might be using log n bits or something of precision. So you do want to make sure you account, when in my presentation to focus on the main idea, we didn't talk about the number of bits you needed to do with FFT. I assume it's log n and the value of the thing. So once you start accounting for that, it might take like n log square n time to multiply integers together. Where n log n is what we just did, assuming you can do arithmetic in log n time, but you might need like log n bits or something. And stuff, or maybe anyway. So it's n times some log squared, log cubed n, something like this. And then as of 50 years ago, Strassen actually is going to come up in a moment for one last application, or one last divide and conquer. But he started doing things like doing things modulo a certain prime number, a large enough prime number, but it kind of keeps the bits down and playing this kind of game. And so he was able to get it to n log n as of like 50 years ago. Again, that's far more detail than we're too concerned with in this class, but it's good to know about. And only recently, in the past like 5 years, from what I can tell, we finally got it down to n log n. Okay, but this was like a randomized algorithm. It seemed very complicated, and yeah, I mean, you're just fighting for like bit complexity and stuff, right? So it's pretty grungy. But nonetheless, you can do n log n randomized for multiplying integers together, and it is going via the fast Fourier transform. But somehow it's opening up. It's very very careful about how many bits you're using where, and it's mostly mathematical observations to kind of get rid of those small order terms. So FFT is very useful. It's also useful for multiplying integers. You can sort of see that from just multiplying polynomials, and you just have to do the paperwork of accounting for bits. Okay, other questions? Okay. Okay, just in case we had time, I had one more example loaded up, which is sort of a historically significant example, although I don't have as good a story for it, so you have to bear with me. Okay, you've probably heard of it. Okay, so the last example I had of divide and conquer is matrix multiplication. Okay, so here I give you two matrices that are square n by n matrices, and you just want to compute their product, which is another n by n matrix. I assume you had to do this in high school for like small examples, and it just takes forever, and you're like, how is this education? Right? But if you're writing loops, the straightforward way to do this, the ijth coordinate, so that's row I, column j. But what you're going to do is you're going to march through row I of A and column j of B, if I got that right. And you're just going to zip it together and make that dot product. First one, second one, third one, fourth one. Okay? And you do that for every entry. So altogether, how long would that take? Like n cubed time, right? And this is why we have GPUs now, because we're over this. But still, so it takes n cubed time. Okay. We have time. So does anyone want to suggest any ideas to do better? Yeah. Oh, can you do a 48? That would be great. Okay, I'm just going to mark that down. I don't actually know where to take this, but basically, can you do FFT at some level? I guess F comes in front. Yeah, so this I think that would be like a dream, but I think we don't quite know how to model matrix multiplication as multiplying polynomials. But I'm also not an expert. There is like a deep end of ever improving algorithms, and maybe more of those ideas have come in. I'm not aware of. Well, maybe we can try a setup that's a little bit more similar to the Karatsuba, which is a little more naive approach. So, I can break, so integers we break in half, but matrices, square matrices, it makes sense to break into 4 square matrices. Okay. And okay, so if it's n by n, then each of these submatrices represent n over 2 by n over 2, right? They're just small squares of this bigger square matrix. And if I multiply these things together, you actually end up doing the same kind of row and column stuff on the block matrices. So it would come out to something like this. Okay, so we could imagine doing like a recursive algorithm where I take my n by n matrix, break each of them into 4 n over 2 by n over 2 matrices, and start multiplying them together and reassembling this. That's sort of like our first Karatsuba attempt, where I kind of broke into bigger and bottom, top and bottom, and then kind of multiplied everything together. Okay. Now, how many of these smaller individual multiplications is required to go into this, at least directly? How many pairs of matrices are getting multiplied together? 8. Okay, so there's 8 multiplies. Okay. And so if we start doing something like T of n is like 8 Tn over 2 plus big O of n squared. Okay. Maybe in the interest of time, I won't do the recurrence tree, but you should end up with n cubed again. Okay, you haven't actually won yet. Just like our first idea for Karatsuba didn't actually improve the running time. Okay. So, but again, this is some situation like integers. Matrices are so simple, they don't seem to have any structure, because it's just numbers. What could you possibly do? Okay. So that's what made the following algorithm shocking in 1969. It might have been like front page New York Times kind of thing. Land on the moon, multiply matrices, like same category. And this is where, I don't have as much to say, but you'll see. Okay, look at this. So, okay, this is a mess, right? But you can at least count how many terms are there. Basically, how many rows? 7. It has 1 less than 8. Okay, so this is 7 rows, each of which, basically is a product of 2 matrices. Some of them do an addition first, but addition is fast, right? Because it's just linear time or n squared time. We're trying to beat n cubed. So you do some additions and subtractions and stuff, but otherwise you're multiplying n over 2 by n over 2 matrices together. Okay. And so Strassen observed that you can rewrite this, okay, as a combination of these 7 things. Okay. There is a certain perspective invoking the word tensor where this might be somewhat natural. Okay. But at least I think on first pass, you can, if you wanted and you had the time and you were really, if you were such a personality, you could go and just at least directly verify that these work out. I did it once and I regretted it. Okay. So this is correct and you can verify it. Okay. But this is an example of taking 8 multiplications down to 7. Okay. So we can work through the recurrence tree. Okay. So if I modeled this, first, what would be the recursive model equation? 7t of n over 2 plus n squared O of n squared really represents linear time because it's a dense matrix of n by n. Yeah. Okay. So I think I'm using n to represent like the one dimension of a square matrix. So they're really n by 2 by n by 2 with n squared over 4 individual numbers inside. Yeah. So maybe it would have been more proper for me to write n comma n, n over 2 comma n over 2, but it'll always be the same. So I'll just write one of them. Okay. Now, if we do the recurrence tree, okay, then, I have a problem of size n. Now I can't even draw 7 lines. 7 lines, I hope, of size n over 2. Okay. And each of these will break out into some 7 lines of n over 4. Okay. And I'll keep going. Okay. So what would be the total amount of work from that first row? N squared. Okay. What about the second row? It's going to get a little more complicated. 7 over 2? Not quite 7 over 2, but it's close. 7 what? Yeah, 7 n squared over 4. So it's getting squared, which is where the 4 comes in, because it's n over 2 squared times 7. So you'll get 7 n squared over 4. Okay. And then what would the next row be, if you can imagine? Yeah, I think it'll be 49 over 16, which is 7 over 4 squared times n. So in general, you're going to get 7 over 4 to the I n. Okay. How tall is the tree? Yeah, n squared. How tall would the tree be? Log base 2 of n. All right, so we get some summation that looks like 7 over 4 to the I times n squared. Yeah. And then how do we evaluate this? It's like our third time in the class or second time? It's going to be dominated by the largest term. So you get 7/4 to the log square n times n squared. Okay. I'll just go slowly. 2 to the log 2. Oh no. 7/4 times log 2 of n times n squared. Something like this. Okay, I'll be quick in the interest of time. So this divided by 4, that's going to give you a -2. Like log 2 of 4 is 2. And that'll cancel out this squared term. And meanwhile, 2 to the log base 2 of n will bring the n down here. Okay, so if we did this correctly, you'll get n to the log base 2 of 7. Okay, which whatever number that is, it's less than 3, right? Because log base 2 of 8 is 3. So we do better than n cubed. This is called Strasson's algorithm. Okay, question.
Do we have to just like short work every time when we swap the 7/4 like the like 7/4 logic just that?
No, I think if you're smart enough to just go from here to up there, I think that's okay.